Okay, so recording started. Um, okay, so hello everyone. Welcome to another week of the series seminars. Today we're going to have Noah Golowich presenting. And Noah is a PhD student at MIT, advised by Konstantinos Daskalakis and Ankur Moitra. I think he's about to graduate soon. And his research interests are broadly in machine learning theory, with like some focus on multi-agent learning, game theory, online learning. Like he's had many contributions, and as you can guess, he also has some contribution in error theory, which he's going to talk about today. Supported by various fellowships, Fanny and John Hertz Foundation, NSF, as well as an MIT Akamai fellowship. And I think today is going to talk about how linear Bellman completeness can be leveraged to achieve efficient learning. So Noah, thank you for joining, and you can start.
Thanks. Can you see my slides okay?
Yes.
Okay, great. So I'll be talking about computationally efficient RL with linear Bellman completeness, and thanks for the invitation to give this talk. And this is joint work with Ankur Moitra. Okay, so I'll begin by discussing some background on MDPs, then I'll discuss the setting of linear Bellman completeness and our algorithm and give you some idea of how we prove our upper bound. So let me begin with a quick overview of MDPs, which are used to model reinforcement learning problems. So in this talk, I'll consider finite horizon Markov decision processes, or MDPs. And these are specified by the following components. So first of all, there's a horizon capital H, an action set A, and a state set S. There's an initial distribution D, which is some distribution over states. There's a transition kernel P of S prime given SA, which says if we're in state S and take action A, what is the probability of transitioning to the state S prime? Finally, there's a reward function R of SA, which gives the reward that the agent receives if they're in state S and take action A. A trajectory in an MDP consists of a total of capital H steps. So initially, at the first step, a state S1 is drawn from distribution D. And at each step, little h, from 1 to capital H, the agent then observes its current state SH, and it chooses an action AH to take according to some policy. The agent then receives reward R of SH comma AH, given by the reward function, and it transitions to a new state SH plus 1 according to the transition kernel P. So we call a set of H state action reward tuples a single trajectory in an MDP. Now in this paper, we're concerned with learning near optimal policies. So formally speaking, a policy is simply a tuple of mappings pi 1 through pi capital H, where each pi little h maps from states to distributions over actions. I'll let capital pi denote the set of all policies. The value function of a policy, q pi h of s comma a, is simply the expected reward that the agent receives if they start in state S, take action A at step h, and thereafter play policy pi. So we're summing these expected rewards from step little h to step capital H. That's the q value function. The v value function of the policy, v pi h of s, is simply the q value function, q pi h, at the state S evaluated at the action A given by pi h of s. Finally, the value of a policy, or v pi, is simply the expected value of the value function at step 1 under a state S1 drawn from the initial state distribution D. Now our goal is to find a value maximizing policy, which we'll call pi star. So pi star is the argmax over all policies pi in the set of policies of v pi. So the goal in online reinforcement learning is typically to find a policy pi hat whose value is near optimal. And we do this via interaction with the MDP over several repeated episodes. In particular, for some number t, denoting the total number of episodes, we're going to iterate from little t equals 1 to capital T. In each episode, we choose a policy pi t based on what we've observed in prior episodes. We then execute pi t and observe a trajectory consisting of states, actions, and rewards drawn from the policy pi t. And then we use this data to choose a new policy pi t plus 1 for the subsequent episode. After a total of capital T episodes, we output a policy pi hat, which should be near optimal. And generally speaking, we want to minimize the number of episodes T. Then we'll think of the number of episodes as the sample complexity, because the number of samples is basically a fixed value, namely the horizon times the number of episodes. Okay. Please feel free to speak up with any questions. I can't actually see the chat, so someone's going to have to read a question if there's.
Yeah. So just to clarify, so here you consider time homogeneous transitions. I guess we're going to.
Say again.
Like here, the transitions are stationary, or?
Yeah. So good question. In this talk, I've kind of written things that the transitions are stationary, but in our paper we deal with non-stationary transitions as well. So it can change from for each step little h. Yeah, I'm not sure how to see the chat, so I guess I can't see anything.
No, don't worry.
We'll monitor that. We'll monitor that. Yep.
Great. Okay. So now let me begin motivating the definition of linear Bellman completeness. So one major challenge in reinforcement learning is that we have to deal with environments with enormous state spaces. This includes things like game playing and robotics. And in such settings, it's not even clear how to represent the policy. So typically, this is approached using the framework of function approximation in reinforcement learning, which proceeds as follows. We're going to first compute some value function q hat mapping from state action pairs to real numbers. And you should think of this as some sort of estimate of the optimal value function q pi star. In practice, these value functions may be computed by neural networks. In theory, when we have trouble proving end-to-end guarantees about learning neural networks, we'll choose some q hat belonging to some fixed function class. Given q hat, we can then use the greedy policy with respect to q hat, which at a state S simply takes the value maximizing action according to q hat. Now, what we hope is that the optimal value function q pi star is well approximated by some class of functions we can learn. Once again, in practice, this might be neural nets. In theory, we have to focus on simpler function classes like linear function classes. And given that q pi star is indeed approximated by such functions, the main question is, how do we actually find such a good approximation? So to answer this question, one important observation is that q pi star, the optimal value function, satisfies the Bellman equation. In other words, q pi star at any state action pair SA is simply equal to the reward at SA, R of SA, plus the expected value of the optimal value function at a subsequent state S prime, which is drawn according to the transition kernel P of SA. And this Bellman equation is simply an instantiation of the dynamic programming algorithm for computing an optimal value function. Now, the quantity shown in red here, this expectation over states S prime, is often known as the Bellman backup of the value function q pi star at step h plus 1. And we'll denote it by t q pi star. And the operator t, which maps a value function q pi star at step h plus 1 to a value function t q pi star at step h, is often called the Bellman operator. So the idea behind, the rough idea behind a lot of works in reinforcement learning, that is dates back several decades, is to use this approach known as value iteration. And the idea behind value iteration is essentially to perform dynamic programming in an approximate sense. First, we want to find an estimate q hat capital H of the value function q pi star at the final step capital H. Then at each step inductively from capital H down to step 1, we're going to estimate a value function q hat h given our estimate of the value function q hat h plus 1. And our hope is that we can estimate this so that q hat h is roughly equal to the reward at step h plus the Bellman backup applied to q hat h plus 1. And this is the equation shown at the bottom of the slide. So the hope is that because the optimal value function q pi star satisfies the Bellman equation, if we're able to approximate this Bellman equation at each step of the value iteration procedure, then hopefully the value functions q hat h will be good estimates of the value functions q pi star. Okay, so I've repeated the definition of the Bellman backup at the top of the slide, since I'll be using it a lot throughout the talk. Now, the main question then becomes, given that we're going to use some procedure like value iteration, how does one estimate the Bellman backups, T, Q hat H plus 1 in the process of value iteration. Typically, this is done using something like least squares value iteration, which fixes a function class script f of bounded complexity, and then given Q hat H plus 1, chooses Q hat H so as to satisfy the following regression problem. We're minimizing over functions QH belonging to this fixed function class f. We're trying to make QH of SA close to an empirical estimate of the Bellman backup of Q hat H plus 1. This empirical estimate takes a single sample S prime. We're looking at Q hat H plus 1 and S prime for a best action A prime at that state, plus the immediate reward. Now, the hope is that Q hat H plus 1 is solved by this regression problem is roughly equal to the reward plus the Bellman backup of Q hat H plus 1. And now an important question is, when is this actually true? So it's been known for a few decades. So in particular, this paper by Munoz and Sepesvari observed that if the data set D, which consists of state, action, reward, state tuples, and which is used in this regression problem, is sufficiently exploratory, meaning that in some sense it explores all possible state-action pairs, then it suffices for this regression problem to be well specified. Now, what does well specified mean? It means that for any possible value for the value function Q hat H plus 1 in the class F, the expectation of the labels in this regression problem, which is simply the Bellman backup, so T of Q hat H plus 1, itself belongs to the class script F. And this property is known as Bellman completeness. It specifies a sort of closedness property for the value function class F. If we take something in the class F and we take its Bellman backup, we get something in the class F. And so Bellman completeness is really a fundamental condition, and that it allows things like this procedure of least squares value iteration to yield near optimal value functions, assuming, of course, that we have an exploratory data set. Now, in this talk, our goal is to come up with computationally efficient algorithms. And as such, and the reason for this is basically that in practice, we don't have good algorithms for learning nonlinear function classes, even in more basic supervised learning settings. And so because we're looking for computationally efficient algorithms, we're going to take the class F of functions to be the functions that are linear in some known features phi of the state action pairs. And when we restrict F to be linear in this sense, we get the condition of linear Bellman completeness. So what I've done the last few slides is a motivated Bellman completeness, and in particular linear Bellman completeness. They're starting with this general procedure of least squares value iteration, saying that Bellman completeness is what we need in order to make this work. Let me now kind of condense the definition of linear Bellman completeness and give a more formal and precise definition of it. So as I mentioned, we're given some feature mapping phi, mapping from state action pairs to d-dimensional vectors. And we say that an MDP M satisfies linear Bellman completeness with respect to the features phi if there's a mapping T from RD to RD, as well satisfies the following requirement. What we want is that for all state action pairs SA, and for all vectors theta which index a value function, the Bellman backup of theta, so that's going to be the expected value of S prime drawn from P of SA, of this linear value function induced by theta. We want that Bellman backup to be a linear function in phi of SA. And the coefficient of linearity is this vector T of theta. So you should think of T of theta as basically being analogous to the Bellman operator. It takes a value function indexed by theta, and maps it to this Bellman backup, which is the value function indexed by T of theta. We also want the rewards to be linear. So R of SA is an inner product between phi of SA and some fixed vector W. Okay, so I gave some motivation in the previous slide for why Bellman completeness is an important topic. But you might ask, well, why does linear Bellman completeness matter? Is this an interesting condition if we restrict the class F to consist of linear functions? And one of the nice things about linear Bellman completeness is that it unifies a lot of the settings in reinforcement learning and control theory where we have computationally efficient algorithms. So in the simplest case, we have the tabular MDP setting, which is the setting where the state and action spaces are sufficiently small that we can write down the transitions and reward information in a table. Obviously, in real-life environments, S and A are not small. And to account for this, a lot of works have studied generalizations of the tabular setting, most notably the linear MDP setting. Here one assumes that the transitions are linear in the features. And in particular, this implies the transitions are low rank. In particular, the rank at most the dimension D of the features. Now, while there's a lot of nice work one can do about linear MDPs, this low rankedness of the transitions precludes certain natural models like linear dynamical systems. So we have efficient algorithms for learning linear dynamical systems, as well as controlled variants of them. And that does not lie within the umbrella of linear MDPs. Linear Bellman completeness unifies all of these settings.
Yeah, just to add, there's another canonical example that falls in linear completeness, but is not a linear MDP. So this is where you have an MDP that admits a non-trivial bisimulation state abstraction. And that abstraction itself, when you viewed it as a linear feature, it satisfies Bellman completeness, but that generally doesn't necessarily put any structural assumption on the underlying. Well, it does put it, but it's not a low rank assumption on the transition. So it's also like, it's linear completeness like set minus linear MDP.
Oh, okay, cool. I actually hadn't seen that. So
yeah.
You said it was bisimulation?
Yeah, I can send you the paper where we showed that. It's actually not pretty easy.
Okay, cool, thanks. Any more questions? Okay, so actually kind of along the lines of that comment, one of the more general reasons for linear Bellman completeness is that maybe we can come up with other general abstractions or general purpose algorithms that work in all of these settings, as well as potentially new settings as well. So of course, one of the main goals here is generality.
Yeah, no worries. I'm just sending that reference.
Okay. Okay, so now let me discuss some prior work on learning MDPs with linear Bellman completeness. So one of the most basic results is that an epsilon optimal policy can be learned with a number of samples that scales a polynomial in the dimension, the horizon, and 1 over epsilon. And there's a bunch of works dating back to 2017 and also some more recent ones that show that this is the case. The problem is that all of these procedures are computationally inefficient. And roughly speaking, this results because they solve a certain non-convex optimization problem, which I'll discuss a little bit more in detail later on in the talk. In light of this inefficiency, there's been a line of work which has aimed to get computationally efficient algorithms for learning linear Bellman complete MDPs. One of these papers by Zanet et al. Shows a computationally efficient algorithm under a condition known as reachability. And roughly speaking, what reachability means is that you assume that there exists a policy which visits feature vectors that point in any direction of Euclidean space. The problem is that reachability is a very strong condition. For instance, humanoid robots can't fly. So if there's a feature direction which corresponds to your robot flying when it can't fly, then you're not going to have reachability. A separate line of work has aimed to get computationally efficient algorithms with deterministic transitions. But despite this prior work, the general problem of coming up with an efficient algorithm for arbitrary MDPs that satisfy linear Bellman completeness has remained open, and that's the main point of this paper. So before discussing our main result about this question, I want to say a few words about why we should care about computational efficiency, even in the linear setting. And roughly speaking, what this question is asking in the linear setting is whether having a good representation or feature map of the state action space is enough to perform efficient reinforcement learning. And one way I like thinking about this is to imagine some alternative universe where linear regression were not computationally efficient. If that were the case, you might expect that it's harder to get efficient algorithms for even nonlinear settings and regression-related problems. And in some sense, reinforcement learning, at least RL theory, is kind of living in this sort of universe where we don't know if very natural problems involving linear RL actually have computationally efficient algorithms. And now this lack of full understanding about linear RL is not due to a lack of effort. In fact, there's been a lot of works that have aimed to understand what linear function approximation assumptions enable efficient reinforcement learning. So all of these works assume the existence of some known feature mapping phi. And They assume various forms of linearity with respect to phi, the features phi. So the weakest type of linearity is linearity of the optimal value function q pi star. It turns out that if all you assume is that q pi star is linear in the features phi, then there are statistically efficient algorithms if the number of actions is small, but there's no computationally efficient algorithm even if the number of actions is even equal to 2. So if we want efficient algorithms, just assuming linearity of q star is not enough. On the other hand, as I mentioned, we can get computationally efficient algorithms in the setting where the transitions are linear in phi of SA, and this is known as the linear MDP setting. The problem, of course, is that the linear MDP dynamics are low rank, and so this fails to model many natural problems. I think of linear Bellman completeness as lying in a sort of happy medium. On the one hand, it generalizes linear MDPs, and it's also a special case of assuming that the optimal value function is linear. And as I mentioned, some prior work shows there are statistically efficient algorithms, and it's open and generally computationally efficient algorithms. So at least, if we're hopeful, we may be able to get efficient algorithms for learning linear Bellman complete MDPs. Okay, so now I'm going to state our main result. What we show is that there's an algorithm that learns an epsilon optimal policy of an unknown linear Bellman complete MDP using a number of samples that scales up as a polynomial in the dimension of the feature map, the horizon, the number of actions, the 1 over epsilon, and it's exponential in the number of actions. And it uses the same amount of time. So in particular, when the number of actions is constant, we get a polynomial time algorithm. Now, the main challenge to prove this theorem is how do we perform the task of exploration? In other words, how do we adaptively explore new states? If we can do this and obtain some data set D consisting of state, action, reward tuples, we can then use this data set in the context of least squares value iteration. So each step little h, we're going to compute this solution q hat h to the least squares regression problem given q hat h plus 1. And the hope is that these q hat h's that we compute will be near optimal. So that's the rough idea of the challenges, namely exploration. I'm now going to give an overview of how our algorithm works to prove this theorem. So our algorithm is a variant of the LSVI UCB algorithm, which is typically used to learn in linear MDPs. And there's some particular aspects of our algorithm which make it similar to the policy search by dynamic programming, or PSDP algorithm. So we call our algorithm PSDP UCB. The way it works is as follows. We're going to set some number capital T of episodes. And for each episode little t, we're going to look at each step little h from the final step capital H all the way down to 1. And we're going to do the following. Roughly speaking, what we're going to do is we're going to draw a bunch of samples and perform some sort of regression so as to estimate the value function at step h. So the samples that we draw are from a uniform mixture of policies, pi hat 1 through pi hat t minus 1. These policies are generated at previous episodes of the algorithm. And the number of samples is some integer n. Given these samples, which we'll call SGI, AGI, RGI from g equals 1 to h, and I from 1 to n, I'll let sigma ht denote the covariance matrix for the feature vectors at step h given by these samples. We're then going to use sigma ht to construct an exploration bonus function. I'll call this FHT. So this maps from the state space to the non-negative real numbers. And roughly speaking, FHT should be larger at states whose feature vectors point in directions that we have not well explored up till episode t. And the reason that this is helpful is for each step g bigger than h, and for each sample I, we're going to define an optimistic reward at step g in sample I, which I'll call RGI hat, which is simply the true reward plus the exploration bonus function FGT at that state. And so if the state is not well explored, we're going to increase this optimistic reward, and that should hopefully induce us to explore similar types of states in future episodes. So what we do is we're going to take these feature vectors at step h, phi of phi h, and we're going to use them as the covariance in the regression problem, where the labels are given by the sum of the optimistic rewards from step h plus 1 all the way to capital H. And this is basically akin to doing some sort of optimistic least squares value iteration. and then we're going to let W hat be the result of this least squares regression problem. So W hat should be thought of as some sort of estimate of a value function. And I'll finally let pi hat TH be the greedy value function, greedy policy with respect to this estimated value function. So its definition is shown in blue here. So this is how I define the policy pi hat t at episode t. I do this for a total of capital T episodes. And at the end of this procedure, I'm going to output a uniformly random policy from pi hat 1 to pi hat t.
And just to clarify, this, I guess you're going to delve into how you define the bonus, but so far the framework looks identical to LSVI UCB, correct?
It's a little bit different. So in LSVI UCB, we actually, as the target to the regression problem, we're going to be using the value function.
Oh, I see. It's actually Monte Carlo rollouts. Okay.
Yes, we're actually using
Monte Carlo rollouts plus bonus.
Plus bonus, yes.
Okay, got it.
Yeah, but that's the main difference. Oops. Okay. So as I said, the main missing piece here is how do we construct the bonus function FHT. And ideally, this should induce us to explore a wide variety of states so that the value functions will be near optimal, and therefore the policies that we use will also be near optimal. Okay, so in the rest of the talk, I'm going to delve into more detail on how we construct these bonuses. The way I'm going to do this is I'm first going to talk about some general principles that we want to use to construct exploration bonus functions. So in general, we really want to satisfy the following 3 requirements. The first is that our bonus is sufficiently large so as to guarantee a property that I'll call optimism. What this means is that the estimate we have of our value functions, I'll call this V hat at the state S, plus the bonus should be an upper bound on the optimal value function of the state S. This is basically a key component in basically any proof you're going to see that uses optimism for getting provable guarantees in RL, or uses exploration bonuses to get any guarantees in RL. Now, a trivial way to satisfy this constraint is just to set the bonus to be the maximum possible value at all states. That's not very useful. So we need an additional constraint on our bonus, and this is that the bonus at a state will actually decrease as we explore that state more. So these 2 requirements, namely that the bonus is not too small and not too large, are in some sense in tension, and a key challenge is to trade off these bonuses, trade off these requirements in the right manner. Now, one of the more challenging things about learning with linear Bellman completeness is that we actually need our bonuses to satisfy a third property. Recall that when I was motivating linear Bellman completeness, the main motivation was that we wanted the regression problems in the context of least squares value iteration to be well specified. Now, in our algorithm, we're going to be regressing value functions or rewards plus bonuses onto feature vectors. And so we want the mapping from state action pairs to the expected value of the linear value function plus the bonus to lead to a well-specified regression problem. In particular, this mapping should be linear in the features. Now, we've already required that the mapping from SA to a linear value function is linear in the features. So really what we want is the following requirement, which says that the Bellman backup of the bonus at some of the bonus function is linear. And that's the requirement I've written here.
And this is why the usual quadratic bonus doesn't work, because it breaks linearity.
Yes.
Yeah.
Yeah, so our work is the first to deal with balancing all 3 of these issues simultaneously with a computationally efficient manner. Okay, now, before I tell you exactly how we define our exploration bonuses, let me say how some of the prior work has defined exploration bonuses. So one approach which actually does work is to choose policies by solving a certain non-convex optimization problem. The constraints of this problem say, in some sense, how do we find the ideal exploration bonus which satisfies all 3 of these requirements? And this gives statistically efficient algorithms, which I discussed a few slides ago, but this is computationally inefficient because this optimization problem does not have an efficient solution. On the other hand, as was just mentioned, a sort of opposite approach to this global optimism approach is to do local optimism, which adds exploration bonuses to each state of size, which is determined by how well explored each state is. And this size is chosen in particular so as to satisfy the first two requirements in the gray box. And while this works for linear MDPs, it fails in the setting of linear Bellman completeness because it fails to satisfy this Bellman completeness property. Now, our work, the main contribution of our work is to design a different type of exploration bonus that actually allows us to make local optimism work for linear Bellman complete MDPs. Okay, so how do we do this? I'm going to use as a starting point the exploration bonuses that look like those that are used for linear MDPs. In particular, to a first order approximation, roughly speaking, what one does for linear MDPs is you define a quadratic exploration bonus, which I'll call FH quad, which is defined as the maximum over all actions of the norm of phi of SA as measured with respect to the covariance matrix of observed features prior to episode T. So for feature vectors phi of SA, which point in better explored directions, sigma inverse, or sigma to the minus 1/2 times that feature vector is generally going to be smaller. And so this quadratic exploration bonus will be smaller. Now, of course, this fails to satisfy this Bellman backup being linear condition. So we fail this third requirement, and so it doesn't seem that this will work for us. A possible fix for this is to use a different type of bonus, which has appeared under various names, such as randomized least squares value iteration. And I'll denote this alternative bonus as FH normal of S, which draws a vector W from a Gaussian distribution with covariance matrix given by sigma HT inverse. And we're going to look at the inner product between W and feature vector phi of SA at this state S. It's trivial that this satisfies the desired linearity property because we've assumed that the Bellman backup of linear functions is linear. And we're just taking an expectation over linear functions induced by W. So by linearity of expectation, we indeed satisfy this third requirement. And moreover, one can show that the normal exploration bonus, FH normal, is in some sense an approximation to the quadratic exploration bonus, FH quad. Won't be precise about how this is, but roughly speaking, it follows because we're drawing the vector W from this Gaussian distribution with covariance sigma HT inverse. So in light of this approximation, you might think that the first and second requirements are also satisfied. But it turns out that there's a very subtle issue that comes up, which is that if we were to use FH normal as our exploration bonus, this will lead to exponential compounding of bonuses. Let me give some rough explanation.
Sorry, before we even go there, so I don't even see, so for example, if we consider a degenerate case where there's only one action, right, and the quadratic bonus would still make sense.
Yeah.
But here, if you remove max A, don't I get a 0 out of it?
Yeah, exactly. So the key point is that when there's one action, there's really no way that you can mess up at that state. Like you're always going to be taking the optimal action. True,
but then, but the thing is that you're doing backups, right? And in your case, like you're doing row outs and adding bonus rewards to all rewards in the row outs, and then estimate a value at the beginning, right?
Yes.
And as you said, like we need optimism. So I don't care about like what actions I choose later on. I need the value I estimate to be, like above V star. For sure.
Yes.
So then the bonus, the value estimate, like it still matters, right? Like even if later on there is a state with only one action. Yeah. But here, like I'm just basically adding 0 bonus to that state.
Right. So you're absolutely right that you are adding 0 bonus. On the one hand, our estimate of the reward at that state is going to be fairly accurate because we get the correct reward. The place where we might mess up is if there's, say, 2 actions at some state, we take the wrong action and our policy ends up visiting a suboptimal sequence of states. And the point of what the randomized bonus ensures is that if there's 2 actions and one of them has much higher optimal value than the other action, then if we end up taking the wrong action at that state, we're going to add on a bonus.
You're going to compensate for that.
Difference.
I see. So is it fair to say that because the quadratic bonus, people also use it with dynamic programming type algorithms, right? Not like Monte Carlo rollout based like PSDP type. So this one you have is like more specialized to PSDP algorithms.
Exactly.
Because if you work with like if you plug it into like DP type backup, it probably doesn't make sense.
Yes, exactly. So if you were to plug our like this randomized bonus into like non-rollout based algorithms, then it would not.
Okay, cool.
Yeah, but good question.
Yeah.
Any more questions? Okay, so as I mentioned, the main issue is that this randomized bonus actually leads to exponential compounding of bonuses. Now, why does this occur? Well, if we have, the point of a bonus in some sense is to cancel out the regression errors that we make at each step. And just a standard guarantee of linear regression tells us that the size of the regression error in the regression at step h is going to be proportional to the size of the labels at step h plus 1. And the size of those labels will grow with the size of the bonus at step h plus 1. In order to cancel those out, we actually need the bonus at step h to be roughly a poly d factor larger than the size of the labels, i.e. the bonuses at step h plus 1. And so we get that each step, the size of the bonus has to be a poly d factor larger than the size of the bonus at the subsequent step. When you iterate this over capital H steps, you end up with something that has to be at least d to the h. And of course, that's way too large to get efficient algorithms. So the way we deal with this exponential compounding is by a form of truncation. And a key component of our truncation is to use what I'll define to be the truncated linear bonus. So given orthogonal vectors u and v and rd, as well as the state S, I'm going to define the truncated linear bonus at state S for the vectors u and v to be the sum of 3 terms. The first is the maximum over actions of the inner product between u and v of SA. The second is the same thing for v. And the third, we're subtracting off that same thing for u plus v. I'll then define the actual bonus we use FHT of S as roughly speaking the expectation of this truncated linear bonus over vectors u and v drawn from appropriate Gaussian distributions. Roughly speaking, the covariance matrices of these Gaussians are given by the span of well-explored directions and the span of not so well-explored directions, respectively. I'll say a little more later about how precisely those matrices, sigma explored and sigma unexplored, are defined. But first, I want to give you some intuition as to how this truncated bonus allows us to avoid exponential blowup. So typically, say in the setting of linear MDPs, the way that one avoids exponential blowup is to use truncation with a constant. In particular, the bonus that one actually uses is the minimum of f quad and the maximum possible value, which is just h, the number of time steps. The problem is that if we were to try to use such an approach in our setting, say take the minimum of the normal confidence bonus in the previous slide and some fixed value h, that would break the linearity property. This new bonus that's truncated with a constant would no longer have Bellman backups, which are linear. Now, roughly speaking, the subtraction off of this third term in the definition of the truncated linear bonus, in some sense, simulates taking a minimum of the first 2 terms. And this rough simulation actually only holds if u and v lie in a certain good region of RD. And what we'll ultimately show is that they lie in this good region with probability that scales inverse exponentially in the number of actions. So this ultimately is why we end up with exponential in A dependence on our in our guarantees. Okay, so this is an overview of kind of why we're able to avoid exponential compounding. Now let me go into a little bit more detail on how we choose our exploration bonus, or why our exploration bonuses actually kind of satisfy these 3 requirements. In particular, I have to tell you how these 3 requirements are formalized. So what does it mean that our bonus is large enough to get optimism? And to do that, I'm first going to define these covariance matrices, sigma explored and sigma unexplored. More formally speaking, they're scalar projections onto well-explored and unexplored subspaces of feature vectors. And the way we define them is as follows. We're going to choose some threshold. I'll call that sigma threshold. We'll let sigma explored be up to a scalar factor, be the projection onto the span of eigenvectors of the covariance matrix sigma ht with eigenvalue at least sigma threshold. And then sigma unexplored is going to be the projection, a scaled projection of the span of eigenvectors of sigma ht, whose eigenvalue is below this threshold. Okay, so given that, I can now formally state what properties I want our bonus to satisfy. The first two properties say the following. In order to show that FHT is large enough to get optimism, what we need is that it's at least the maximum over all pairs of actions A and A prime of the minimum between two terms. The first term is the distance between phi of SA and phi of SA prime as measured in the unexplored subspace. The second is simply the distance between phi of SA and phi of SA prime. And for the upper bound, I want a similar bound where I'm only taking a maximum over single actions and I'm looking at the two analogous distances. The first is measured in the unexplored subspace. The second is measured with respect to the Euclidean norm. Now, there's a slight difference between these bounds in that the first bound, the lower bound, is taken over a maximum of pairs of actions. And in the second, we're taking a maximum over actions. This relates to the question from a few minutes ago about dealing with the difference between actions and dealing with states with a single action. But I'll kind of gloss over that particular distinction in this talk. And I want to focus on a different aspect, which is how you should interpret the minimum, each of these terms in the minimum. So roughly speaking, the term, which is sigma unexplored times the features phi, should be thought of as an analog of the quadratic exploration bonus in the context of linear NVPs. Recall that the quadratic exploration bonus was upweighting feature vectors, which point in more unexplored directions. And that's exactly what we're doing here. We're basically actually downweighting all well-explored directions to 0 and upweighting all unexplored directions to some fixed scalar constant. The red term on each of these bounds should be thought of as an analog of truncation. In the setting of linear MDPs, we truncate with a fixed value h. It turns out you can be a little bit more refined than that by noting that the optimal value function is a linear function in the features whose coefficient vector is going to be a bounded norm. So just by using Cauchy-Schwarz, you can upper bound the value function by a fixed value times the norm of the features at each state action pair. And this is why we can use the norm as opposed to h in order to do our truncation. And of course, the third requirement is that we want an FHT, which satisfies these upper and lower bounds, but it also has Bellman backups that are linear. And as I defined FHT in the previous slide, this third requirement is actually immediate. So I won't really need to discuss that anymore. Finally, I want to add one more wrinkle to this, which is that it turns out that we can actually relax the first requirement of this problem. Instead of truncating with the distance between phi of SA and phi of SA prime, we can actually truncate with their distance as measured by this unexplored projector, sigma explored. The reason for this is a little bit technical, namely our algorithm actually used the modification of the bonus's FHT. It has a small multiple of the projection of the features phi into the unexplored subspace added onto it. And so we can basically decrease FHT by an analogous projection into the unexplored subspace, which leaves us just with the projection into the explored subspace. And that's roughly speaking why we can actually relax this requirement. But for now, you can just think of us as trying to satisfy these three requirements. So next, let me tell you why the bonuses that I defined a few slides back actually indeed satisfy these requirements. I'm going to focus on the special case where the number of dimensions d is 2 and the number of actions is also 2. And suppose for simplicity that the unexplored subspace is spanned by some vector v, and the explored subspace is spanned by some vector u, which is orthogonal to V. So formally, the matrices sigma explored and sigma unexplored are given by UU transpose and VV transpose. A few slides back, I defined the bonuses FHT as an expectation of the truncated linear bonus, which I've shown below this orange box, over vectors u and v drawn according to some Gaussian distributions. The thing is, when the explored and unexplored subspaces are each single dimensional, this expectation of Gaussian distributions basically degenerates into saying that we're going to take an expectation over signs that's plus or minus 1 multiplying each of u and v. This is because we can basically normalize things to be of unit norm. So really what we want to show is that FHT of S, which I've written as a sum over all possible signs multiplying u and v of the truncated linear bonus, satisfies the two requirements in the gray box at the top of the slide. Once we write things like this, the proof actually becomes pretty simple. It turns out that by shifting all feature vectors by a fixed constant, we can assume that one of the feature vectors, say phi of S comma A0, is equal to 0 at every state. And then we just have to evaluate the truncated linear bonus at each pair of signs epsilon u and epsilon v. So I've given an example here where we take epsilon u equal to 1 and epsilon v equal to minus 1. And we can now just write out what this thing is. So the first term, shown in blue, as a maximum of actions which will be achieved at the action A1 for these particular choices of u and v. The second term is attained at the action A0. And it turns out that we can always choose the signs multiplying u and v, so that the third term shown in red is always non-positive. So for this particular example, you can easily check that u minus v has non-positive inner product with each of the two feature vectors. Now, you can simplify this expression knowing that the term in green is 0 because phi of S comma A0 is the origin. And eventually what we end up at is the distance between the two features, phi of SA0 and phi of SA1, as measured in the unexplored subspace, the explored subspace sigma explored. If you were to do a similar thing with a different choice of feature vectors, you might end up with sigma unexplored as opposed to sigma explored in this lower bound. But in either case, we verify the first requirement, which is that FHT of S is lower bounded by the minimum of these two quantities. And the upper bound is similarly immediate. One can just use a direct computation, so I won't go through that. So showing that this bonus FHT satisfies the two requirements is pretty straightforward when the number of actions is 2. You can actually generalize that argument to when the number of actions is 3. Unfortunately, this breaks when the number of actions is 4. And let me just tell you the counterexample because it's fairly simple. If we have a state S whose feature vectors phi of SA are arranged in a rectangle, whose sides are parallel to the explored subspace spanned by U and the unexplored subspace spanned by V, then it's straightforward to check via direct computation that the truncated linear bonus, the state S, and the vectors U and V, even if they're multiplied by signs, is equal to 0. On the other hand, the first requirement of the truncated bonus problem requires that the bonus at state S is strictly positive. This is because if we look at two diametrically opposed actions, as shown on the left-hand side here, the distance between those two vectors has strictly positive component in both the explored subspace, that's the horizontal one, and the unexplored subspace, that's the vertical one. So this lemma actually becomes false as soon as A equals 4. How do we get around this? Well, it turns out that we can actually use a weakened version. We can actually aim for our bonus to satisfy a weakened version of the truncated bonus problem. In particular, I'm going to weaken the first requirement, the lower bound, by only requiring that this inner minimum be taken over vectors psi belonging to the convex hull of feature vectors of the state S. So in particular, we're looking at a maximum over pairs of actions A and A prime, and a minimum over vectors psi. And we're going to look, first of all, at the difference between phi of SA and psi as measured in the unexplored subspace. And second, the distance between psi and phi of SA prime is measured in the explored subspace. One can recover the previous requirement by restricting psi to either equal phi of SA or phi of SA prime. But because we're now allowing psi to lie over this whole convex hole, we actually get a much weaker lower bound. And so if we go back to this problematic instance that posed an issue for the previous problem, namely where the 4 feature vectors are arranged in a rectangle, once again, the truncated linear bonus is going to be 0, which requires that FHT of S is 0 by my definition of FHT of S. But the nice thing is that this weakened truncated bonus problem actually allows FHT of S to be 0. This is because if we take, once again, 2 diametrically opposed feature vectors, so on opposite vertices of the square, and if we choose psi to be the action at the lower left-hand side of this rectangle, then when we move from psi to phi of SA, we're orthogonal to the unexplored subspace. And when we move from psi to phi of SA prime, we're orthogonal to the explored subspace. So each of those 2 terms in that inner minimum is equal to 0. And so in this way, this rectangle no longer poses a counterexample to satisfying the weakened truncated bonus problem. Of course, one actually has to prove that the bonus that I defined, namely this expectation of truncated linear bonuses over U and V drawn from appropriate Gaussians, actually satisfies these 2 requirements. But it turns out that you can actually do that. And roughly speaking, the idea is to reduce to a 2-dimensional problem where similar reasoning to the previous slides actually applies. And so in particular, we can get this lower bound, the first requirement, if U and V lie in a certain good region that is exponentially small mass in the number of actions. Okay, so up till now, I've told you why the bonuses FHT of S satisfy the first and second requirements here. Now let me say a few words about how we can go from those requirements to getting to showing that we actually get a near optimal policy. And this part of the proof is a little bit more standard, so I won't say that much about it. The rough idea is as follows. Recall that pi hat t are the policies that are explored by our algorithm, or chosen by our algorithm. And I'm now going to find optimistic value functions associated with the policies pi hat t. So for each t, I'm going to define an optimistic q value function, q bar t at a state action pair, which is equal to the immediate reward plus the expected value of rewards and bonuses from step h+1 to capital H. I'll then let v bar t be the value of q bar t at the state S, where the action is given by the choice of pi hat t at state S. So what we can show using the first item of this weakened truncated bonus problem, which says that our bonuses are sufficiently large, is that with high probability, we actually get optimism. So v bar t plus our exploration bonus at any state S is an upper bound in the optimal value v pi star S. And roughly speaking, the reason that we get this is because our bonus is adding on a sufficiently large component in the unexplored feature vector directions. The second lemma that we can show using the second item of this weakened truncated bonus problem is that the bonuses FHT of S are bounded above by the norm of the features phi of SA as measured with respect to the inverse covariance matrix sigma ht to the -1/2. And so once you have those 2 lemmas, you can put them together in a fairly standard way. What you can show is that the average over all episodes t of the difference between the optimal value function v pi star and the value function of the actual policy we choose v pi hat is bounded above by, first of all, the difference between the optimistic value function, so v bar 1 plus ft1, minus the actual value functions, v pi hat of t. And this just uses the first lemma, so optimism. And once we have that, we can simply use the fact that the value functions is the sum of expected rewards. The optimistic value function is the sum of expected rewards plus the sum of expected bonuses. The expected rewards cancel out, and we end up with a sum of expected values of the bonuses under the policy pi hat t. Finally, using this upper bound on the bonuses FHT of S, together with the elliptic potential lemma, we're able to upper bound the penultimate term by something that decays as 1 over root t. And that's how we're able to show that the policies pi hat t that we choose are actually optimal. Okay, so I can conclude here. I guess that's maybe a good place to finish. I'll kind of quickly advertise a different paper that we have where we consider an offline reinforcement learning problem with linear Bellman completeness. And what we show is there's actually a polynomial time algorithm that has no dependence on the number of actions. And we're able to get a policy that scales with a single policy coverage condition in the offline reinforcement learning setting. And one interesting feature is that our guarantee actually scales with the square root of the misspecification error in the more general setting of learning with linear Bellman completeness, learning with low inherent Bellman error, which is a generalization of linear Bellman completeness. So let me conclude. What we've come up with is the first computationally efficient algorithm for online reinforcement learning with linear Bellman completeness, when the number of actions is constant. And in this companion paper, we have the first algorithm for offline reinforcement learning with low inherent Bellman error. Maybe the main open question is extending our algorithm or finding a lower bound when the number of actions is larger. So basically avoiding this exponential dependence on the number of actions. And there's some interesting questions in the offline setting as well. So thank you for listening.
Nice. Excellent.
Yeah, thank you.
Yeah, I have a quick question about the technical part. So, as you show in the last, like proof outline, right? So the exponential dependence mainly come from the, I think the next slide. Yeah, it basically come from lemma 2, right? Because it's essentially saying that it's the bonus is proportional to the usual quadratic bonus, but up to like a huge like exponential like constant in front of it.
Yes.
Right. And you know, once you have that, like the rest is like just the standard like ellipsoid potential argument, but just plug in that like constant. So, but I don't quite get how you get lemma 2. Like previously you mentioned this, like, you know, good area happens with probably dh to the negative a. Like, yeah. Can you say a little like more about that part again? Like, how does that lead to lemma 2?
Oh yeah. So basically, what we're actually doing is when we define this thing, I have a factor right here, which is going to be like dh to the a. So I'm actually scaling this up by dh to the a. And and so once you have that scaling up, then kind of lemma 2 is actually immediate from this condition.
Oh, okay.
Because I have a dh to the a here, and then the unexplored will go to 0 as we.
Yeah, I guess maybe that's what. Yeah, I guess my intuition, like it's related, is like, you know, when you have no action, it's you get it. Sorry, when you only have one action, is 0, right? So you're basically like relying on the max, like that order statistics thing, to get like, you know, a little bit of non-zero value. So in general, if you don't multiply anything, like the bonus will tend to be like pretty small, or
if you don't multiply, yeah. So if you don't multiply this bonus by anything, then you'll like. Requirement 1 will only be satisfied like up to a factor of dh to the minus a. And like that won't be enough for optimism. So we actually have to like scale up all the bonuses in order to make requirement 1 satisfied by like the right factor. Okay. When we scale them all up, that's why like we get this dh to the a right here.
Yeah, another thing that comes to mind is you know, like this exponential in a dependence seems closer related to like you need to do max over a all the time. So instead of like say linear completeness for a Q star, have you considered something of the like, for example, linear completeness for V star? Or maybe coupled with a policy class or something of that kind.
Like I think you could consider like policy completeness. So like if you have a policy class and you assume linear completeness for that policy class. I guess like there actually have been some paper, like there have been some other papers that like if you assume Q pi is linear for all pi, there's like some papers that do this in the like maybe it's computationally inefficient. I haven't thought about kind of other way, like other variants of this assumption, but I think they'll end up looking a little bit like these like linear QPy papers.
Right.
Actually, there I guess it's also open to come up with computationally efficient algorithms. So it's a good point that maybe like some of our techniques might be useful in those settings as well, because it's kind of analogs of like Eleanor there, and like there's these open problems as well. So.
So I think I also have a question, because so I don't get in the end which is the dependence on epsilon of the sample complexity when you find them. You said that with the elliptical potential lemma you can get basically this term going as 1 over square root of t.
Yep.
But if I saw correctly at the beginning of the talk, you mentioned that you get 1 over epsilon also with the exponential dependence on the number of action.
Yes.
Can you tell me a bit about this?
That's a good point. So actually, like, this is a slight lie here. Like, it's not actually like poly dha over root t. It's actually going to be something well, there's basically going to be kind of one error term that I haven't written here, which relates to the fact that we have to kind of split this covariance matrix into well-explored and unexplored directions. There's going to be some error parameter epsilon there. So there's some epsilon outside, and then that epsilon also comes up in this bound as well. So there's some trade-off between epsilons, and ultimately we do indeed get like epsilon to the minus a.
Okay.
So this is an oversimplification because there's additional error terms that I haven't written here.
Yeah. Okay. And you think this was dependence on epsilon is a price to pay for having computational efficiency, or?
That's a good question. I don't know about like epsilon, so I think it's maybe plausible that you can get like say like dh to the a times epsilon to the minus 2. Like I think that's actually maybe plausible instead of having like epsilon also be raised to the minus a. I'm a little more skeptical about getting rid of the exponential in a altogether.
Okay.
I think it's a little more likely there's a lower bound, but I'm not sure.
Yeah, thanks.
Yeah, actually, like, do we know hardness about like whether this exponential in A is inevitable in this setting or not?
No, so that's the main open question.
Okay.
I've tried to come up with a lower bound, but it's hard to construct linear Bellman complete MDPs that are not linear MDPs. That's kind of the main challenge.
Yeah.
Also, I think Zach, in his linear QPy paper, has an exponential dependency in the dimension, not the action.
Yes.
And he was also wondering, is there a lower bound exponential D or something in that setting?
Okay, but he uses a slightly more general setting. It's not.
Yeah, it's not the same setting, right? It's like for linear QPy.
Oh, it's linear QPy. Okay, so yeah, isn't there a paper by Ruzong and others that gets some lower bounds? Maybe it's in the offline setting.
Oh, I don't know.
Like from 3 or 4 years ago, there's a linear QPy paper with exponential lower bounds. I think that's maybe offline. And that actually motivates like having policy completeness for offline.
I stop the recording here.